Hi everyone, welcome back. In this lecture, we're going to look at examples from other areas of the natural sciences and social sciences. Now, we're really not going to be introducing anything new here, no new techniques. What we are going to be doing is we're going to be looking at these examples from other disciplines where they don't actually use the term derivative when they talk about a rate of change. They either use the term rate of change or they use other words that represent a rate of change or a derivative. And so we're just going to become familiar with some other disciplines and the kinds of terminology they use when they talk about derivatives. So let's go ahead and look at our first example. And this one comes from physics. Now, if you scan quickly through the question, you'll see that at no place does the word derivative appear. And of course, you're very well attuned now to the fact that whenever you see the word velocity and acceleration, well, those actually mean derivatives. So it's not so hard to see in this example that we're going to have to compute some derivatives because we are familiar with the terminology used in physics and its relationship with calculus. We'll see some other examples in a bit which may involve terminology you're not used to from these other disciplines. So let's go ahead and look at this one. The example of a motion for a particle is given by this equation. So S is its position and t is time. So this is telling us at any given time what the position of a particle is. Now you can think of this as your particles moving along a straight line, this s-axis. And this s-axis has two directions. There's in this case, the way I've drawn it here, there's a right direction and a left direction. But we'll instead refer to these as positive direction and negative direction. So this positive direction is indicated, well, if I have a 0, then where's 1? Which side of 0 is 1 on? And if 1's over here, which typically we draw on horizontal, 1 is on the right, then this is now our positive side, or our positive direction. And this is our negative side. So we've got this particle, and it's moving in this line. And its position at any given point is given by this function over here. Now, what do we want to know about it? Well, we'd like to know what the velocity and accelerations are as functions of t. We're going to graph some stuff about its position, velocity, and acceleration. We want to figure out when it's speeding up, when it's slowing down. So let's get a good visual for what's going on here before we start our calculations. So what I've done is I've put a particle, a little red point, on this s-axis, and I've allowed it to change in time. So as time changes, you can see the particle's position is changing. The other things I've indicated here are at the given position, what is the corresponding velocity and acceleration. The direction of the velocity is given by the arrowhead. The length of the arrowhead is the magnitude. So the longer the arrowhead, the higher the speed. And so let's just click and play our motion. Now it's going to head off the screen for a little bit, and then it'll come back and restart. So every time it comes back to the origin, it's restarting. And you can see that from the time interval here. So it's restarted. So it's moving to the left, and then it slows down, stops, and then moves to the right. And it's going to be quite hard to see. I've got all these things changing. When is it moving right, left, stop, speeding up, slowing down? So I'm going to inch by inch go through this. So let's reset it back to 0. And now let's step through this. So originally, the velocity and the acceleration are pointing to the left. So it's moving to the left, it's accelerating to the left. And then it's still moving to the left, but it's accelerating to the right. What's happening in this case? Well, this indicates that it's slowing down. So these are the kinds of things I want to really tease out of this example. How do we figure out where a particle's speeding up? How do we figure out when it's slowing down? And this illustration here is telling us what we need to look for, essentially. So, okay, now I'm going to keep going. It's still moving to the left. You can see that by the velocity. And then all of a sudden it comes to a stop. And now it starts to move to the right. And you can see that it's accelerating to the right. You see the acceleration arrow there, pointing to the right, but it's also moving to the right. And you can see the velocity arrow is increasing in length. So we'll back it up a little bit. The velocity arrow is increasing in length. That's because it's speeding up. So its velocity is increasing in value. Okay, so let's go back and reset. Back to the origin. And we're starting off again. position is given by red, my velocity and acceleration functions are computed there, their values, and all I care about are their signs, in some sense, for knowing which direction it's moving, which direction is accelerating. So it's moving and accelerating it to the left, now it's moving to the left, accelerating to the right, then it's moving and accelerating to the right. And so looking at those arrows again, we'll reset. It's speeding up because it's accelerating, moving in the same direction. Oh, now it's moving in one direction, accelerating in the other direction, so it's slowing down. And now it's moving and accelerating in the same direction, so it's speeding up. All right, so I wanted to just implant this sort of visual in your head so that we can go ahead and work through these calculations and at least have a mental picture for what we're working with. Okay, so find the velocity and acceleration functions. Let's go to work. The velocity function, well, that's the derivative of the position function. Position function here is this degree 3 polynomial, so its derivative is 6t squared minus 6t minus 12. What's our acceleration function? Well, that would be the derivative of the velocity function, which is also the second derivative of the position function. And so that's 12t minus 6. So that's part A done. We found our velocity and acceleration. Now B is asking us to graph all of them. Well, we've already got the sketch of the graph of the position function here. I've got this strange number 3 plus root 105 over 4. That's really this root here. How do we figure that out? Well, if we had to do it without having the graph there, what we would do is we would look at the position function and say, well, there it is. Ah, look, there's a common factor of a t in every term. So factor out that common factor of a t, so that becomes 2t squared minus 3t minus 12. So what are the roots of this function? Well, one root comes from this linear factor t sitting out front. So that's t is 0, that's one root. What's our other root? Well, we've got two roots now, possibly two roots as the roots of this quadratic. So what are those roots? Well, that'll be the quadratic formula. I mean, we can use the quadratic formula on this. So that would be negative b, so that's 3, plus or minus the square root of b squared, that's 9, minus 4, a, c. And all of that is all over 2a, which is 4. And what's inside the square root? That's 9 minus, and then 4 times 2 is 8. 8 times 12 is 96. Two negatives cancel off, plus 9. So that's 105 under the root. So there's where that 3 plus root 105 over 4 came from. The other root, 3 minus root 105 over 4, that's a negative number. So it's going to be on the negative part of the t-axis, and we don't care about that. We're only looking at graphing it on the interval from 0 to 4. And the function itself is only defined for positive t values. Okay, so we've got our position function sketch. What about our velocity function? Well, there's our velocity. It's a quadratic. We can factor out a 6 from each to make it look a little bit nicer. Oh, and now I can see that this thing factors really nicely as a t minus 2 and a t plus 1. So we've got our roots. They are t equals 2 and negative 1. I only care about the root 2. When t is negative 1, that's not under consideration. It's not even in the domain of my function. So there's our roots. What also helps to graph, in this case it's a quadratic, so a parabola, is to know what its vertex is. The vertex we can get, well, if we know two roots, then the vertex is going to be right in between them. So what I can do is I can average these two roots and get the t value for the point right in between them. So the average of 2 and negative 1, 2 plus negative 1, that's 1, divided by 2 is a half. So our vertex is a half. Plugging a half into our velocity function, we get negative 27 over 2. So there's our vertex. It's a half and negative 13.5. So let's go ahead and jot this down here in red. So our Point is about negative 13.5 and a half. So there's our vertex. We know it's a parabola opening upwards. It's got a root here at 2. And where does it hit the vertical axes? Well, I can plug 0 into our velocity formula here. And I get a value of negative 12. So it's going to pass through a point right about here. So it comes down, hits our vertex, turns around, goes back up, and shoots off like that. So there's our velocity function. Next, we have our acceleration function. And that's this linear function, 12t minus 6, which we can write as 6 times 2t minus 1. And just to be consistent with everything else we've calculated, we can look at the root, and the root here is 1/2. So it passes through this point here. It's a line of positive slope. Slope is 12. It passes through the vertical axes at negative 6, so somewhere around here, and it shoots off like this. And so there's A. Now, there's lots of connections between these graphs, of course. Let's work from the position function all the way up to acceleration. So for our position function, if I look at this point here, that's a place where the tangent line is horizontal. But the slope of the tangent line is the velocity function. And so we see where the tangent line is horizontal, that's precisely where the velocity function crosses the axes. Where the velocity function has its vertex, or horizontal tangent line, that's where the acceleration function is crossing the axes. So there's these nice connections between these graphs because they're derivatives of one another. Okay, so what's next? We've plotted them. Now we want to figure out where the particle is speeding up and slowing down. Now if we think back to that applet we looked at, there was something involving direction of velocity and direction of acceleration, and whether they pointed in the same direction or not as to determine speeding up and slowing down. Now this is a very critical observation that we have to make because it is the basis of a lot of misconceptions that students have regarding speeding up and slowing down. So I want to be very careful in dealing with this here. The main point is that velocity and acceleration are vector quantities. They have a magnitude and they have a direction. The direction is given by the sign of the corresponding quantity. So what does sine of v and a mean? So what does it mean when velocity is negative? What does it mean when acceleration is negative? What does it mean when they're positive? Let's quickly jot these down. What does it mean when the velocity is positive? Well, velocity is the rate of change in position, so it means the position is increasing in value. That means the particle, let's look back at our horizontal line here, if I have its position, no matter where it is here, if it's increasing at value, it means it's moving in this direction, in the positive direction. It's moving in the positive direction. To the right here, because I've drawn it horizontally. But we could look at examples where maybe a stone's being dropped off a cliff, in which case the particle is moving along a vertical line. And so this notion of left and right doesn't make any sense anymore. There we were talking about up and down. So to be completely general, I'm going to say that when the velocity is positive, it's moving in the positive direction. If the velocity is negative, it means the particle is moving in the negative direction. So velocity positive means that the particle is moving in the positive direction. What happens when the velocity is negative? I'm going to use a lot of ditto marks here. So the particle is, and I'm going to still write the word moving because I'm going to contrast it with acceleration, in the, and here's where the difference happens, negative direction. So when the velocity is positive, it means it's moving in the positive direction. When the velocity is negative, it means the particle is moving in the negative direction. What about the acceleration? Well, when the acceleration is positive, it means that the particle is accelerating in the positive direction. And when the acceleration is negative, that means that the particle is accelerating in the negative direction. I'll use ditto marks on that one. Ditto. So that's what sign is telling us. Velocity and acceleration are vector-valued quantities. Sign is indicating the direction of motion. Okay, so what does it mean to speed up? What does it mean to slow down? Well, if the velocity is positive, it means it's moving in the positive direction. If the acceleration is positive, it means it's accelerating in the positive direction. So both of them are pointing in the same direction, both positive, so it has to be speeding up. If they are opposite in sign, if it's say moving in one direction but accelerating in the other direction, then it's got to be slowing down. It's moving, 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 but it's accelerating in this direction, so it's slowing down. So when they're opposite directions, velocity and acceleration, then it's slowing down. When velocity and acceleration are in the same direction, it's speeding up. We'll jot that down in a second. But what that means is in order to figure out that problem of where this particle is speeding up and where it's slowing down, we need to know the signs of the velocity and acceleration. And we can get that from these graphs. All I'm doing here is plotting the t-axes and the points that are of interest, where there's a possible sign change in either my velocity or acceleration function. So this is a half, 0. This is 2. And there's this 3 plus root 105 over 4. That was where the position changed value, changed sign. I don't really need that when I'm considering my velocity and acceleration. So I can ignore that one for now. And let's look at velocity and acceleration. What are the signs? So here's our sign chart. I'm just going to indicate the interval here and then jot a little either plus sign or minus sign depending on whether the velocity is positive or negative. So here it's negative. Then it's still negative on that interval. And then after 2 it switches to positive. Whereas my acceleration is negative to start with, and then after a half it switches to positive, and it stays positive. And it stays, both of these stay positive then forever, forever onwards, off to infinity. So what we have here is that on this interval and on this one, there's the particle is speeding up. Whereas on this one, it's slowing down. So here we go. Question C. Particle is speeding up when V and A have the same sign. And when does this occur? We've already indicated up here on the interval from 0 to half and the interval from 2 to infinity. The particle is slowing down when V and A have opposite sign. And when does this occur? Well, this occurs when t is on the interval from 1/2 to 2. Okay, so we found out where it's speeding up and where it's slowing down. Notice that that agreed with our animation here. V and A are pointing in the same direction. It's speeding up, speeding up, speeding up, and then once we hit a half, now the acceleration is pointing in the opposite direction, so it's accelerating to the right, but still moving to the left, so it's slowing down, slowing down, slowing down until we hit 2. Then it starts speeding up, and it speeds up forever as t moves on. Okay, so one thing I want you to notice here is that right at the beginning, we can see it's speeding up. And note, its acceleration is negative and its velocity is negative. So both of them are negative. Remember, the sign just tells us direction. Acceleration is negative, velocity is negative, speeding up in the negative direction, speeding up to the left in this case. Now this is one of the misconceptions that comes to show itself when students are working on problems of speeding up and slowing down. The most common misconception is that students believe a particle is speeding up when the acceleration is positive. But that's not the case. We've just seen that here. Acceleration can be negative. It's still speeding up because it's moving in the negative direction as well. But this misconception is rooted in something that actually is true. And I leave that as an exercise to you. So instead of looking at the velocity function, let's look at the speed function. Strip off the sign from the velocity and look just at the speed function. This speed function has the property that the particle is speeding up when the rate of change in the speed function is positive. This is not the acceleration, notice. This is not acceleration. Acceleration is the rate of change in velocity. This quantity here is the rate of change in the speed. So I leave this as an exercise to note that if you look at just the speed function, then yes, the rate of change in the speed function, the sign of that is enough to tell you speeding up or slowing down. However, when we're looking at the velocity function and trying to figure out speeding up or slowing down, we need to look at both the signs of velocity and acceleration to determine that. Okay, so I leave that part as an exercise to you, dealing with the speed function. And note, in order to solve that problem, you're going to have to use the fact that speeding up happens when velocity and acceleration are in the same direction, and slowing down happens when velocity and acceleration are in opposite directions. Okay, there's one last question to deal with here, and that is this one up here. What does the expression s triple prime of t, which is the derivative of the acceleration function, what does that represent? So d. Oh, let's put it back in blue. D. S triple prime of t, which is the first derivative of the acceleration. What does that represent? What does it mean? Do we have a name for this? Now, the only point I want to illustrate with this is that you may have thought when we're working on derivatives that these higher derivatives, second derivative, third derivative, etc., may not have necessarily had any good meaning in terms of applications. Well, right now we're seeing that, well, the second derivative, that means acceleration. So there is an application of the second derivative. And the third derivative, well, in physics, the third derivative of the position function for a moving particle is called the jerk. And you can actually feel this if you're in a car and you're moving and you have a rate of change in your acceleration that isn't constant, then you feel it by this sort of jerking motion. Right? So there you feel a third derivative. You feel one of these higher order derivatives. And that is given the appropriate name of jerk, just because of that jerking motion that you feel. All right, so that's it for this example. We'll look at a few other examples from chemistry, economics, and then one from mathematics itself.